Hello, welcome back. Lecture 2. Today we're going to be talking about comparative advantage. I assume that you are here because you are in my class, but if you are not in my class, then hey, maybe consider buying my book, Principles of Microeconomics, a step-by-step guide to principles of microeconomics. It will teach you how to do all the sorts of problems that you will see in your microeconomics course. But that said, let's get on to comparative advantage. So, Let's first take a bit of a recap from what we talked about last time. We went through three basic principles of economics, right? We talked about the scarcity principle, which tells us that we are always going to have some sort of trade-off in front of us, right? We can't have everything that we want. So we gotta, if we want something more of something, we gotta give up something else. So there's going to be trade-offs that we're going to have to deal with. And when there are trade-offs, that's when economists are going to swarm in and tell you what to do. And what we're going to tell you to do is follow the cost-benefit principle. Cost-benefit principle, if you remember, says that if you are trying to decide what to do in a particular situation, how to make a choice, what the economist would tell you that you should do, the way that you should make those choices, is to choose the option for which the benefits most exceed the costs. All right? We've always got benefits and costs, and we need to compare them to the proper alternative in order to figure out what we're going to do, right? So those benefits and those costs are not just going to be the direct costs and benefits. If you remember, right, the direct costs and benefits are the stuff that you touch, the stuff that you actually do. But you also have to take into account the indirect costs and benefits. Those are the things that don't happen, right? If you were choosing between two different candy bars and you know you're going to enjoy either of them, and you pick the Snickers over the Crunch Bar, one of the costs of picking the Snickers is that you don't get to enjoy the Crunch Bar, right? That's an indirect cost, because it's a cost that you're paying basically because something nice didn't happen, right? Your opportunity cost. You're giving up the opportunity to eat that Crunch Bar. So in addition to the cost-benefit principle, which tells you how you should be making decisions, we also have the incentive principle, which tells you how people do make decisions. And again, just like the other two, this one is fairly common sense. All it basically says is, if you want people to do something, you need to improve the incentives for doing it, right? People follow incentives. They're making decisions on the basis of the incentives that are available to them. And so if you want them to make a decision in a particular way, or if you are going to try to get them to do it or something, then you need to improve the incentives. So if you make the benefits greater for one of the options that are available to people, they're going to be more likely to pick it. If you make the costs greater, they're going to be less likely to pick it. Right? People are going to follow those incentives. With all that in mind, we're going to introduce one more principle, and that is the comparative advantage principle. Now what this one is about is how to allocate the tasks. Right? There's lots of stuff in the world to be done. There's lots of stuff to be made or farmed or produced or just chores that you have to do in your house. And so we have the question, how should we decide how we're going to do those things? Who is going to do each of those different tasks, right? How are we going to allocate those tasks to different people or different companies or different countries or whatever it is, right? There's stuff to be done. Who's going to do it? And what the comparative advantage principle says is that we're going to do the best, meaning we're going to most effectively and efficiently use the resources that we have if the way that we allocate those tasks is to make sure that everyone concentrates on the activity which is for them the most productive relative to the other activities. Again, this one is fairly common sense to start out with, but there's a lot more to it. And a lot of it's hiding in that little phrase right there, relative to other activities. So what does that mean exactly? It means that when we're thinking about how good you are at something, we can't just think about how good you are at it. We need to think about how good you are at it or how good you would be at the alternative. Right? Cost-benefit principle is basically applying here, right? If we're not just thinking about what kind of stuff we want, right? Do we want the milk or do we want the jalapeno, using the example from last time? But we're also thinking about what should you do? Well, should you spend your time doing task A or task B? You can't really say how good you are at task A unless you're comparing it to the alternative of task B. And when you do that properly, the comparative advantage principle is going to tell you how to most effectively use all the resources that you have available to you. So let's have a basic example. Okay, so let's say that I'm sitting right here and then we bring in somebody else. We're going to bring in a professor from the computer science department. Okay, and she and I have some stuff to do. We're going to work on a project together. And this project is going to require that we write some computer programs, and it's also going to require that we build some economic models. Okay? So one thing that we can think about is, okay, how good are each of us at these two tasks that we have? Once we figure that out, it's going to be a little bit easier to figure out, well, who should work on which of those tasks. So let's say, for example, that if you give her an hour, and she spent that entire hour writing computer programs, she would write 6 computer programs. Okay? That's how productive she is at making computer programs. If you, instead of having her spend that hour on computer programs, you had her spend that hour making economic models, she would make 2 economic models. Okay? And similarly, we can think about how productive I am at each of these things. And if you put me on making computer programs for a whole hour, I would write 2 computer programs. And if you put me on the task of making economic models, in 1 hour, I would produce 6 economic models. So we're going to write this down in a little table. It's going to make it a little bit easier to keep track of everything. So we're going to have her over here, and we're going to have me over here. And we have 2 tasks for each of us. And so we have the prospect of building some computer programs. And we could also spend our time building economic models. And we're going to fill this in. For her, if she spends her hour on computer programs, she's going to write 6 computer programs. If she spends her time instead on models, she's going to make 2 models. If I spend my time on computer programs, I will end up with 2 programs. And if I spend my time on models, I will end up with 6 models. All right, so we have this little table here that's going to tell us basically how productive we are at these different tasks. So let's say that these are our levels of productivity and we have a job before us. So let's ask this question. Let's say that we have to produce a certain amount of stuff. How long is it going to take us? So let's start out. Let's first say that we're working independently. Okay, that each of us have to make 2 programs and 2 models. Let's say so she has to make 2 programs and 2 models. I have to make 2 programs and 2 models, and we're working independently. So we can't specialize and focus on the thing that we are good at. Right? We're just working independently. So how long is it going to take each of us? All right. So 2 programs and 2 models. For her, if she can make 6 programs in an hour, that means that each one is going to take her 10 minutes. And so making 2 programs will take her a total of 20 minutes. Okay? And if she can make 2 models in an hour, then making those 2 models she needs to make is going to take her an hour. So an hour plus 20 minutes is going to take her an hour and 20 minutes or 80 minutes to make 2 programs and 2 models. Same thing for me. So I'm going to spend 1 whole hour making my 2 programs because I can only make 2 programs an hour. And since I can make 6 models an hour, each one is going to take me 10 minutes. So to make 2 of them, that's going to be 20 minutes. So it's going to take her 80 minutes to make 2 programs and 2 models. It's going to take me 80 minutes to make 2 programs and 2 models. So we got the amount of stuff that we needed, and in total it took us 80 minutes each to get there. Okay? So that's if we're working independently. What's going to happen if we do what's called specialize and trade? So what I just showed you, where it took us 80 minutes, that was the no trade version of this problem, right? We're each working independently. Everything that we're going to make and need, we need to do ourselves. We're completely self-sufficient, okay? And there's no trading going on. We don't care about the other person. We're just working independently. Another word for this is called autarky, with a K, autarky. Anyway, so we did that. Now let's think about specializing and trading. So instead of each of us having to be self-sufficient, we can specialize in just the thing that we're good at. And then whatever else we need, we can trade with the other person. So obviously, in this case, right, she is better at writing computer programs. I am better at writing economic models. And so she's going to go ahead and specialize in computer programs. I'm going to go ahead and specialize in economic models. And then once we have what we need, all we need, we can trade with each other to get the 2 programs and 2 models each that we need to have. So let's figure out how long this was going to take. So when it was autarky, when it was no trade, it took us 80 minutes each. Now, if she needs to make 4 computer programs in total, so she can have 2 and I can have 2, that's going to take her 40 minutes. Each one takes her 10. She needs 4 of them. That's 40 minutes. Similarly for me, we need 4 economic models. Each one's going to take me 10 minutes to make, so it's going to be 40 minutes for me. She makes 4 programs, I make 4 models, we trade, we'd have the exact same amount that we had before, 2 and 2, but it only took us 40 minutes each. So we basically just halved the amount of time that we need to spend on this. We got the same amount of stuff. which is another way of saying we're using our resources more efficiently, right? We got the same amount of stuff with less work. So that frees up, we can take that other 40 minutes and spend it on whatever we want. We can relax, we can make more stuff and improve the standard of living in this economy that's based on economic models and computer programs. Whatever we want, right? We just became more efficient. And that's a general rule. And that's what comparative advantage principle is going to get us, is that if we specialize on the things that we're best at, right? We don't make her waste her time on economic models when she's so good at computer programs, then we're going to end up with more stuff overall. And that's just one way of looking at it, right? We started out thinking, okay, we need to make this certain amount of stuff. How long is it going to take us? Well, let's flip that around and let's say we have a certain amount of time. How much stuff can we make? Okay. So let's fix our amount of time that we have available at 40 minutes, right? We both walk into the room, we have exactly 40 minutes available to us, and then we got to go somewhere. So how much stuff could we make? Let's say that we wanted an equal amount of computer programs and models. If we were working independently, again, no trade, autarky, it would take my whole 40 minutes, I would get one computer program and one model, right? Each program takes me 30 minutes, each model takes me 10, and so I get one of each. She would do the same, right? Each program would take her 10 minutes, each model would take her 30, she would get one of each. Now compare that to what we got with 40 minutes before when we were specializing in trading. Instead of one each, we got two each. So again, we sort of became more effective in the same amount of time, the same amount of effort and input, we ended up with twice as much stuff. And that's the magic of comparative advantage. Now, all this so far is probably not that surprising to you, right? You take the person who's good at something and you make them do it, and they're going to produce more than somebody who's bad at it. That's not exactly groundbreaking result right there. But the interesting thing comes about not when each person is obviously better at one of the things, but what happens if one person is better at both things? Okay? What happens then? So what's going to happen if one person is better at both of these tasks? And this is going to end up being a little bit surprising. So think about intuitively what you think might happen. Right? You might, for example, say, okay, well, let's say she's better at both computer programs and economic models. Well, probably she should be the one making both of them then, right? That feels like the obvious thing that should happen. But in fact, that is not the case. Okay? And let's see how that works. So the computer science professor shows up, and it turns out she is not just great at writing computer programs, she is also great at economic models. Let's redraw this table here. So instead of making, so she can still make 6 programs an hour, but now instead of 2 models, she can make 3 models. Now for me, I can now make, let's say, 3 programs an hour, but only 2 economic models. So now we're looking at this table and we can see she's better than me at both of these tasks. She has what's called an absolute advantage in both of these tasks. In both of these tasks, she's better than me, right? She can work faster, she can produce more in a given amount of time. So we need to make some programs and some models. Who should do what? And it's going to turn out that we can assign those tasks on the basis of, again, comparative advantage. Let's show that we can still make some gains here by specializing in trading. So first of all, let's see what happens if we're back to autarky, we're back to no specializing in trading, or no trade. So let's say that each of us wants to get 1 model. So if she makes 1 model, let's see how many programs she can make. So if she makes 1 model, and let's say we have the whole hour here, that's going to take 1/3 of her time. Right? She can make 3 models an hour, so if she makes 1 model, that's going to be 1/3 of her time. Which means that she's going to have in total 2/3 of her time left over to make programs. If she can make 6 programs in an hour, then in 2/3 of her time, she can make 2/3 times 6 programs, or 4 programs. Okay, so independently, she makes 1 model and 4 programs with her hour. How about me? Okay, if I make 1 model, that's going to take 1/2 of my time, which leaves me 1/2 of my time left over to make programs. In 1/2 of my time, I can make 1/2 times 3 programs, or 1.5 programs. So we decided that we each want to have 1 model. Whatever time we're going to have left over, we're going to spend making programs. How many programs can we make? Turns out we can end up with 5.5 programs in total, 4 plus 1.5. So that's without trading. Let's see if we can do better by specializing in trading. So we still want 2 models, but let's say that we're going to give that task to me. I'm going to make the 2 models. Obviously, that's going to take all of my time. I'm out for the count. And then she can spend all of her time making programs. Now, she can make 6 programs in an hour, so we're going to end up with 2 models and 6 programs. That one's pretty easy to figure out. Compare that to how we did without trade, right? Without trade, we had 5.5 programs and 2 models. With trade, we have 6 programs and 2 models. So we're doing a little bit better, right? We're producing more with the same amount of input just by rearranging who does what task. That's all we did, right? We didn't bring in more people. We didn't spend more time. All we did was reallocate the tasks according to comparative advantage, and we ended up with more stuff as a result. We were more effectively and efficiently using our resources. And so how did I get here, right? I told you that in this case, I'm going to be the one making models, but how did we know that I should be the one making models instead of her? We can do this by calculating out what that relative ability is. Now, if you remember back, I told you about comparative advantage principle just a minute ago. I said we need to figure out how good you are at each task relative to the other tasks. So we're going to have to calculate out how good you are, each of us are at these tasks relative to the other tasks. So let's figure this out. The way we're going to figure this out is by calculating opportunity cost. Right? And that whole concept is going to come back. So let's think about what we're doing here. Right? We have a fixed amount of time, and we can spend it either making programs or models. Okay? So what's the cost of producing a program? Okay? What does it actually cost us? Now, there's not really a dollar figure that it costs us, right? We're not spending any money here. What it really costs us is the opportunity cost. We are giving up the opportunity to instead spend that time making models if we want to make a program, right? So how do we calculate out what we're giving up? What is our cost? And it turns out this has a pretty straightforward function that we can calculate out. The opportunity cost of producing a program, in this case, is equal to the loss in models divided by the gain in programs. So why is that? So let's think about it. So let's imagine that we are currently spending all of our time making models. Okay? So let's say that this is me, okay, and I'm spending all my time making models. I'm making 2 models. So then I change my mind, and instead of spending all my time making models, I instead say I'm going to spend all my time making programs. So what happened there? So I went from making 2 models to making 3 programs. So what was the cost of each of those programs? Well, in order to get 3 programs, I had to give up 2 models. So the cost of 3 programs is 2 models for me. So on a per program basis, that is 2/3 of a model, right? Which if we plug this in here, right, the opportunity cost of a program for me is going to be the loss in models, which is 2, right? I'm giving up those 2 models in exchange for the 3 programs I'm going to end up with. So my opportunity cost of producing a program is, like I said, 2/3 of a model. Now that's for me. We can calculate out the same thing for her. The opportunity cost of a program for her is the same thing. If she was spending all of her time on models, she'd make 3 models. If she gives that up and instead spends all of her time on programs, she makes 6 programs. So she gave up 3 models, in exchange got 6 programs. So on a per program basis, she is giving up 3 models in exchange for 6 programs. So that is 1/2 of a model. Okay? So we've calculated out the opportunity cost. And this is not in terms of dollars, this is in terms of what we are giving up. Right? We gave up I gave up 2/3 of a model every time I decided I wanted to make a program. She gave up 1/2 of a model every time she decided she wanted to make a program. Now I did the opportunity cost of programs here. We could do the other way around. We could do the opportunity cost of models for me. Now we just do the same thing in reverse. I give up 3 programs in exchange for 2 models. So 3/2. So the opportunity cost for me of a model is 3/2 of a program. And the opportunity cost for her of making a model, well, she is giving up 6 programs in exchange for 3 models. So her opportunity cost is 2 programs. Now, you might note that these are just flipped upside down, right? How did I get the opportunity cost of models? It's 3/2. The opportunity cost of a program is 2/3. No, that 3/2 is just 2/3 flipped upside down, which makes sense, right? You're comparing the two against each other, right? And so going in one direction, you get 2/3. You go the other direction, you just do it backwards. You get 3/2. So, if you want to go from one opportunity cost to the other, you can just flip it upside down. Super easy. So we've got our opportunity costs. Now what can we do with this? How can we figure out what our comparative advantage is? Who should be the one doing the task? Well, think about, who do you want to do a task? It's the person who can do it the most effectively, the most efficiently, the most cheaply. And we have right here the price of producing a program. So who should be the one who should produce the program? The person who can do it the most cheaply. That is the person with the lowest opportunity cost, right? Who is going to give up the least to produce this program? That's the person who should produce the program. It only makes sense, right? And so let's look at these opportunity costs. The opportunity cost of producing a program for me is 2/3. The opportunity cost of producing a program is 1/2 for her. 1/2 is less than 2/3, and so she has the comparative advantage in programs. Now, again, that's not too surprising. We already determined that she was better at programs than me. But let's think about models for a second. Well, let's look at the opportunity cost of producing a model. The opportunity cost of producing a model for me is 3/2. The opportunity cost of producing a model for her is 2. 3/2 is less than 2. And so I am the one with the comparative advantage in producing models. And interestingly, what this whole process means is that no matter how different the two people are, the two countries or the two firms are, you're always going to have something that you will have a comparative advantage in. It's mathematically impossible, nearly, to not have a comparative advantage. Think about why this is. Well, I just told you about how the opportunity costs basically flip upside down when you go from going in one direction to going in the other direction. That means, well, if we look at the opportunity cost for programs, it's lower for her than for me. So if we take the inverse of both of them, it's going to be higher for her than for me. And so automatically, if she has the comparative advantage in one thing, I have the comparative advantage in the other. Which means, if you let's say we're talking about trade between two countries. Let's say you got a really big country with lots of productive capacity. They can make a lot of stuff. They have a lot of people. They got a lot of factories. They just can produce a whole bunch of stuff. And then you have a little tiny country. They might be good at some stuff, but they can't produce that much, right? They just don't have as much people. So the question is, can there be gains from trade if these two countries trade with each other? And the answer is yes. Right? Even though that big country is better at everything than the small country, simply as a result of having more, power, more available capital, more factories, more people. Even whatever they're best at, it's going to be best at relative to the other things they could be doing, which means that the small country, even though they don't have any absolute advantages, they're going to have a comparative advantage. And because we have a comparative advantage, we're going to be able to increase the amount of stuff we can produce, use our resources more efficiently by assigning the tasks according to comparative advantage. So we've got this idea of comparative advantage. We've got the way in which comparative advantage allows us to allocate tasks most efficiently by calculating opportunity costs and assigning tasks to the people with the lowest opportunity costs. And with all that in mind, let's move on to our very first model. Aren't you excited? So this model is called the Production Possibility Frontier, also known as the Production Possibility Curve. And what this does is it describes all the different mixes of stuff that you could produce. Okay, that's all that it does. It just says, okay, you have this many inputs available to you. What could you do with that, right? You could produce more of this and less of that. You could produce less of this and more of that. And that's all we're doing. We're describing the available options that you have for producing stuff. So let's start with a basic example with our production possibility frontier. We're going to start with two people stranded on a desert island. Their names are Chuck and Wilson. And they have two things they could be doing. They could be collecting coconuts or they could be collecting walnuts. And of course, they need these things to eat. And Chuck happens to be really good at gathering coconuts, and Wilson happens to be really great at gathering walnuts. Right? So I've already slipped it in there that they have comparative advantages. Chuck's going to have the comparative advantage in coconuts. Wilson's going to have the comparative advantage in walnuts. So let's draw out a production possibility frontier. So what we have here this is a single person's production possibility frontier. Specifically, it is the production possibility frontier for Chuck. This describes what Chuck could be doing with his time. So Chuck, we're going to say, is able to gather 15 walnuts if he spends all of his days collecting walnuts. And if he spends all of his time instead collecting coconuts, he can collect 30 coconuts. So this is his production possibility frontier. We have walnuts and coconuts on the y and x axis respectively, right, describing how many coconuts and walnuts he ends up with. And if he spends all of his day collecting walnuts, he collects 15 walnuts, and so we put on the y axis a 15 because that is the most that he could possibly collect of walnuts, right? If he's already spending all of his time on walnuts, he can't spend any more. Similarly, if he spends all of his time collecting coconuts, he can collect 30 coconuts. So we put a 30 on the x-axis because that's the most that he could get of coconuts. So that's Chuck. Let's take a look at Wilson as well. Now Wilson's curve looks very similar, except he's much better at walnuts than he is at coconuts. So in Wilson's case, if he spent his whole day collecting walnuts, he could collect 30 walnuts. If he spent his whole day collecting coconuts, he could collect 15 coconuts. Okay. So you might notice that this sounds pretty similar to the table that we drew out before for programs and models. And in fact, we can draw a similar table. So we have Chuck, and we have Wilson, and we have coconuts, and we have walnuts. Chuck, if he spent his whole day collecting coconuts, he'd get 30 coconuts. If he spent his whole day on walnuts, he'd get 15 walnuts. If Wilson spent his whole day on coconuts, he would get 15 coconuts. If he spent his whole day on walnuts, he would get 30 walnuts. All right, so we have our table. It's the exact same as it was before. And so what we've described here is basically what they could produce individually, right? So, and when we have this production possibility frontier, which really just takes these 2 points that we've drawn on the table and then draws a straight line between them, all that straight line is telling you is how they could be allocating their time, right? We don't know where exactly on this curve they're going to end up. We just know it's going to be somewhere if they're using all their time efficiently, right? If we're looking at Wilson's production possibility frontier, Wilson could decide to collect 30 walnuts. He could decide to collect 15 coconuts. He could decide to be somewhere in the middle. He could mix his time on different activities and end up with some mix, but that mix is going to be on that line somewhere, all right? So, another neat thing about this is going to come if we start thinking about the opportunity cost. We calculated the opportunity cost before. Let's do it again. So let's say the opportunity cost of collecting a coconut for Chuck. We're going to do the exact same way that we did before. If Chuck was collecting all walnuts, he would have 15 walnuts. If he switched to all coconuts, he would have 30 coconuts. And so his opportunity cost of collecting a coconut is 1/2 of a walnut. Similarly, for Wilson, the opportunity cost of collecting a coconut for Wilson, if he had all walnuts, he would be at 30 walnuts. If he went to all coconuts, he would have 15 coconuts. So his opportunity cost is 2 walnuts. Now, an interesting thing about these opportunity costs is they also show up in the production possibility frontier. And specifically, they show up as the slope. If we look at Chuck's production possibility frontier here, you can see that the slope is -1/2, right? Just do a little rise over run calculation, you get the slope is -1/2. And that is also the opportunity cost of Chuck to get a coconut, right? Which makes sense, right? If you're giving up all of the walnuts and you're getting all the coconuts, that's basically rise over run, which is the slope. So the slope encodes that opportunity cost right in there. And similarly for Wilson, the slope for Wilson's production possibility frontier is 2, and the opportunity cost for Wilson to collect a coconut is 2. Now, this is interesting because we can then tell at a glance which of them has the lower opportunity cost, just from looking at the production possibility frontiers, even if we haven't calculated out the opportunity cost. Because we know that the slope tells us what the opportunity cost is. We know that the lowest opportunity cost, and therefore the shallowest slope, is going to be the person with the comparative advantage in that task. So, Chuck has the shallower slope than Wilson. Therefore, Chuck has the comparative advantage in collecting coconuts. And by inverting it, we can say that Wilson has the comparative advantage in collecting walnuts. So that's all very nice. We can also calculate out how much stuff they can get, if they're working independently, that same problem that we had before, right? We're going to want to know how to do this. So let's say that they each want to get an equal number of each type, which, by the way, if you're in my class, I'm not going to force you to know how to do this, but here's how you would do it. So let's say we're Chuck, and we want to see how many coconuts and walnuts Chuck can get if he needs to get an equal amount. So first thing we would do is we would write out as an equation Chuck's production possibility frontier. So what is that? So for Chuck, the number of walnuts that he can collect is at most 15. And for every walnut, or for every coconut that he collects, he is going to have to give up 1/2 of a walnut. Right? So every coconut he adds, he's going to have to give up 1/2 of a walnut. So the slope in there is negative 1/2, right? Just like it is on this graph. If we want him to get an equal amount of each, we just need to set the number of walnuts equal to the number of coconuts. So we got the number of coconuts equal to 15 minus 1/2 times the number of coconuts. And then we could do some algebra. We get 3/2 times the number of coconuts is equal to 15. Multiply both sides by 2/3, and we get that the number of coconuts he can get is 10, which, since we set them equal to each other, we also know that the number of walnuts he can get is 10. And I'm not going to go through the math again, but I can also tell you that Wilson could equally get 10 of each. So if they're working independently, no trade, autarky, each of them can get 10 coconuts and 10 walnuts. It probably will not surprise you to learn that if they are working together and trading, they will end up with more stuff. So let's think about what they're going to do if they are going to specialize and trade. So we already know that Chuck is better at coconuts. We determined both just looking at the numbers, it's pretty obvious, but also in terms of looking at the slope or calculating out the opportunity cost, that Chuck has the comparative advantage in coconuts. So if he spends all of his time on coconuts, he's going to get 30 coconuts. Okay? And if Wilson spends all of his time on walnuts, he's going to get 30 walnuts. And so if we divide that between the two of them equally, it's going to be 15 coconuts and 15 walnuts each. So by specializing in trading, they were able to increase the amount of stuff that they produced. Just like we had with the programs and models example, that by specializing in trading and the things that we are good at, we are going to be able to produce more stuff. But how can we show this on our production possibility frontier? We need to be able to represent it somehow. And what we're going to do is we're going to build what's called a shared production possibility frontier. So just like the individual production possibility frontiers that we already saw describe what each of them can produce when they are working on their own, the shared production possibility frontier is going to describe what they can produce when they are working together, right? When they are specializing and trading. And we're going to be able to draw it in a very similar way to the way that we drew the individual ones. So here's how we're going to do it. So first thing we're going to do is we're going to draw axes just like we had before, right? We're going to have walnuts up here on the y-axis. We're going to have coconuts down here on the x-axis. Now, there's 3 important points that we need to hit, and 2 of them are just like the ones that we already had. So up on the y-axis, what did we have before? Well, we had on the y-axis a y-intercept that showed what was the most number of walnuts that you can get if you spend all of your time on walnuts. That same question applies, except now there's both of them working together. So if both of them spend all of their time working on walnuts, how many walnuts can they produce? Well, Wilson is going to get 30 for us, Chuck is going to get 15, and so in total, together, we are going to end up with 45 walnuts. Same question down on the coconuts axis. They spend all their time on coconuts. How many coconuts are they going to end up with? Well, Chuck is going to create 30, Wilson's going to create 15, and in total, they are going to create 45, and so we're going to have 45 on the x-axis as well. But this time we cannot just draw a straight line between them. We'll think about why that is. Well, the slope of the line represents the opportunity cost. But there's 2 of them now, and each of them has a different opportunity cost. So there have to be 2 different slopes in this curve. So this is not going to just be a straight line, it's going to be 2 straight lines, right? The individual production possibility frontiers joined together at a kink point. So we got 3 points to worry about: the y-axis, which we did, the x-axis, which we did, and the kink point. So let's think about what that kink point is supposed to be. The kink point is the point at which both of them are specializing fully in the thing that they are best at, right? Each of them has a thing they have a comparative advantage in, and they can specialize. And if they are only spending time on the thing that they have the comparative advantage in, that is going to be the point that we're going to have the kink point at. Because that's basically the point where we sort of shift from one person to the other, right? If we're at the kink point, we're basically, let's say we're at the kink point, we're making more and more and more coconuts. And we're going to have, of course, Chuck doing that job of making the coconuts first because he has the comparative advantage. But then we get to the point where Chuck is making all the coconuts he can. If we want any more coconuts than that, we're going to have to start assigning the task to Wilson, even though he's not as good at it. So the point at which we shift over from Chuck to Wilson is going to be that kink point at which we see the slope change. So how many of each of these things are we going to get if each of them is specializing fully? So Chuck is spending all of his time on coconuts. We're going to get 30 coconuts. Wilson is spending all of his time on walnuts. We are going to get 30 walnuts. We follow that point out here. We get our kink point, and then we can just connect the dots and get our nice shared production possibility frontier. You can see that this is, of course, at the point 30 and 30. We can compare this to the 20 and 20 that we were producing before, right, when each of them was producing 10 on their own. And obviously, we have some gains from trade here, right? We're producing more stuff than we otherwise would have done. Something to note with this, as I'm putting it together, we do have this sort of bowing out shape that sort of bulges, right? And there's a reason for that. The reason for that is the way that we arrange this according to slope, right? We want to make sure that the first person who is doing any of these particular tasks is the one who's better at it, right? Let's say we're not making any coconuts whatsoever, but we want to start making some coconuts. Who should we give that job to? Obviously, Chuck. He's the one with the comparative advantage. He's better at it. So we want the lowest opportunity cost to be the first one to do it, and which means that we're going to want these shallow slopes up top and the steeper slopes down at the bottom. Let's start out, in this case, we're doing no coconuts, just like I said. We decide that we want to start making some coconuts. Like I said, we're going to give that job to Chuck. So we can sort of think of this part of the production possibility frontier as being Chuck's part. And this part down here of the production possibility frontier as being Wilson's part. And you know, we start out with the lowest opportunity cost, and that's the shallowest slope up top. And then we go out until we exhaust Chuck. Chuck is already spending all of his time on coconuts. And then we move on to the steeper slope, the more expensive source of coconuts, which is Wilson. And then he starts to be the one who does it. Now this idea, where we are organizing it by shallowest slope, where we're giving the task first to the person with the lowest opportunity cost, this is yet another principle. And this is called the low-hanging fruit principle, also known as the principle of increasing opportunity cost. And this one basically just says that you first use the resources that are best suited to the job. Real common sense stuff. So we want to start making coconuts. We're going to give that job to Chuck first. He has the comparative advantage. Then we're going to give it to Wilson. You can imagine this same principle applying in a lot of other areas. Imagine you are working with farmland. Okay, well, let's say we're trying to grow some grains in the United States. Some parts of the country are really good at growing rice. There's a lot of good rice growing land in the South. So other areas are much better suited to growing wheat. If you look in the Midwest, there's a lot of wheat fields out there. The land is very well suited to growing wheat. Let's say that we're in a world where the United States is not growing any rice whatsoever, but you want to start growing some rice. Well, where should you do that? Obviously, you want to do it in the land that's best suited for it. You're going to run into a lot fewer headaches. The costs of production are going to be lower. You're going to be more effectively using your resources. Imagine if instead you took the land that was the best wheat field you could possibly imagine. The soil is just perfect. The sunlight is perfect for wheat. And you took that away and you made rice instead, right? The opportunity cost there is clearly very high. You're getting rid of a lot of really good wheat land in exchange for that rice. Instead, you should find some land that's not very good at wheat, but good at rice, and use that for the rice instead. That's the principle of low-hanging fruit, and that's going to give us this production possibility frontier where those shallowest slopes go up top. And when we follow this, we end up with these gains from trade, right? Allocating your tasks according to the comparative advantage principle is basically the same thing as following the low-hanging fruit principle. And as a result, we're going to end up getting more stuff out of our resources. And this sort of surplus production is really important That's sort of why we have the standard of living that we have today. It's why we have all this stuff. It's why we're not starving, most of us, all the time. It's why you don't work on a farm. If you go back only a few hundred years, pretty much everybody just worked on a farm. That was life for 99% of people. And now that is the case for like 1% of people in the United States anyway. And the reason we can do that is because we have a lot of surplus stuff, right? That same amount of land, because we have used specialization to make sure that we are most effectively reusing the resources that we have, ensures that we have a lot of extra stuff. So not everybody needs to spend all their time growing food, and they can instead specialize on the things that they are best at. You can sort of imagine how much stuff you would have if you had to make everything yourself, if you had to be perfectly self-sufficient. Well, you certainly wouldn't have a phone. You wouldn't have a radio or a TV. You probably would not have very nice clothes. You probably would not have very nice shoes. And you can think you probably would. Everything you eat would come from a walk's distance from your house because you wouldn't have a car. Your life you just wouldn't have as much stuff, right? Your standard of living would be a whole lot lower as a result. And we need this surplus production. We need to be able to specialize and trade because not specializing, not trading, is the version of the world where you are literally making everything yourself. So we use this increasing opportunity cost principle. We specialize in trade. We end up with this shared production possibility frontier, which lets us produce more stuff than if we were producing on our own, if we were being self-sufficient. And we get the nice things that we have. And we get to eat dinner every night, which is all very good stuff. Now, I've made a bit of a jump here, and maybe you've caught it. I've started talking about the economy as a whole. Right? I've talked about organizing the entire economy, and all we've done so far is talk about two people. Obviously, two people is not the economy. So there's a gap here between what we have on the page and what we are talking about in terms of organizing everything at all times, everywhere. So let's fix that gap. Let's expand this idea of the production possibility frontier, and let's work that up to see if we can say something about a whole economy. So instead of two people, let's talk about three people. Let's say that we have three individual production possibility frontiers. And let's forget about Chuck and Wilson. Now we just got A, B, and C. And so now what we're going to do is we're going to build a three-person production possibility frontier, a shared production possibility frontier. Instead of Chuck and Wilson's, which only had two people, now we're going to have three people. So given these graphs, which of these should go on top of the production possibility frontier? Like we discussed before, the ones that go on top are the ones with the shallowest slopes. And so we're going to take C, we're going to put it up on top. We're going to take B, we're going to put it in the middle, and we're going to take A, and we're going to put it all the way on the right. The resulting production possibility frontier is going to look a little bit like this, which, just like the two-person production possibility frontier, has some kink points in it. Right? It's got one less kink point than it's got people. And it's just a bunch of straight lines joined together at those kink points. And if you wanted to calculate out the numbers that were at those kink points, you would follow the exact same steps, basically, that we did for Chuck and Wilson. But we don't want to stop at three people, right? Two people's not an economy, three people's not an economy either. So let's add four people. Okay, we get to four people. Now it turned the same idea. We just organize it with the shallowest slopes up top. We get steeper and steeper as we move to the right. We have a kink point between them. Let's go from four people to five people. Same idea. We have the shallowest slopes up top, get steeper as we move to the right. And we have a bunch of kink points. As we do this, it starts to look a little bit smoother as well, right? As we get more and more kink points, it becomes less a bunch of blocky lines and more a little bit smoother. And if we keep doing that, we're going to end up getting smoother and smoother and smoother until we end up with something that looks like this. And this is the production possibility frontier for an entire economy. We have this nice smooth line. Again, the shallowest slope up top, and as we move to the right, the slope gets steeper and steeper and steeper. And when you have that, you end up with this nice bowed out, sort of curved production possibility frontier. And what this is you can imagine looking straight in at something like Chuck and Wilson's production possibility frontier, and then adding more and more people and sort of zooming out and zooming out and zooming out as you go from 2 people to 5 people to 1,000 people to 1,000,000 people. And eventually there's just so many kink points that it just turns into a nice smooth line. And this is going to describe the production possibility frontier for an entire country. Each little tiny dot on this production possibility frontier is an individual person. And you can imagine that individual person with their individual opportunity cost all coming together to form an entire economy's production possibility frontier. So that's the basic idea of production possibility frontiers. That's the first model that we have dealt with. And there's one more thing that I want to talk about with this model. And this is going to apply to a lot of the models that we do in class, is that when we just have the model sitting there on the page not doing much, it doesn't really mean much to us, right? It's not going to be that useful. But what we can do with it is try to think about how can this graph move? What's going to move the graph? And that's going to give us more interesting things to say. And this is going to, like I said, go for a lot of the models that we're going to talk about in this class. When they're just sort of sitting there static, they can't tell us all that much, right? If I look at this production possibility frontier for an entire economy, what can I actually learn from it? Well, I could find a point on it and say, well, this is the economy's maximum production, but in order to draw it in the first place, I would need to know what it can produce anyway. So it's only telling me something that I already know. But what we can actually get out of this, the intuition we can get out of this that we don't already have, what is going to happen when we start moving this around. So let's think about what's going to move this production possibility frontier around. Now remember that this production possibility frontier is saying is, given the inputs that we have, this is what we can produce. That's the idea that we're going for. So anything that can change the amount of inputs that we have, or anything that can change how effective those inputs are at creating production, are going to move this graph and end us up with a different looking graph than we had before. So let's do this. Let's draw some examples here. What we're going to do is we're going to start out with our economy-wide production possibility frontier. And let's say instead of doing coconuts and walnuts, we got rice and wheat, like that example that we had before. Now, let's say that something changes. Let's say that, for example, we get a lot more people move into the country. And some of them will go to work in the agricultural sector, right? So we get more people who are working in areas that can produce rice and wheat. So we have more inputs available to us. So what's this going to do to our production possibility frontier? Now, we can produce more stuff now, right? If we think, let's think about it. Let's say we were producing entirely rice. We can produce more rice than we could before. So we know that our y-axis is going to be higher than it was before. How about wheat? Well, if we were spending all of our time on wheat, we could still produce more wheat than we could before. So our x-axis is going to be further out. We draw a nice smooth curve, and we can see that our production possibility frontier has sort of pushed out along all directions. Well, what is this saying? This is basically saying we can produce more stuff than we did before because we have more people to produce it with. Pretty intuitive. We can also think about, well, what will we actually produce? Remember, this just says what we can produce. What will we actually produce? So we can imagine, let's say we were producing this amount right here before, right? We were producing this much wheat and we were producing this much rice. Well, what are we going to do now? Well, we could be sort of at the same point on the curve out here, but we don't have to be. Well, maybe we've decided that we already were making all the rice that we wanted to make. So in that case, maybe we won't move up at all. We won't produce any more rice. We'll just move to the right and we'll produce a little bit more wheat. Yeah, heck, we could decide to produce even less rice than we did before and even more wheat, right? We could change in any particular way. Also, we can think about what might happen if the curve goes in the other direction, right? Instead of a bunch of people moving into the country, maybe a bunch of people move out of the country. We got fewer people to work. That's going to shift our production possibility frontier in, right? Same shift, just in the opposite direction. And that's going to be a change. Any sort of change that changes all the resources that are available to produce either of these goods is going to have a shift on the production possibility frontier that looks like this. But that's not all that we can do, right? Both of these things that we described happen to both of these crops. What if only one of them changes? Let's say, for example, that we have another production possibility frontier. We're going to go with rice and wheat again. But this time, somebody invents a new machine that makes it much more effective and efficient to harvest rice. So for the same amount of effort that you had before, you can harvest more rice. So how is this going to change our production possibility frontier? So, okay, if we were producing all rice before, we're going to make a lot more rice. But if we were producing all wheat before, this doesn't really change what we can produce, right? If nothing's changed about the amount of wheat we can produce, then nothing's changed about the amount of wheat we can produce. And the more rice that we are making, the bigger of a boost we get. So sort of what this ends up looking like is if you put your finger on the wheat axis and then you just sort of stretched up the production possibility frontier along there. So you get these really big gaps over near the rice intercept, and you get relatively smaller gaps over here on the right. Same thing happens if maybe instead of a new machine being introduced that improves the harvest of rice, maybe there's a blight. There's some sort of disease affecting the rice crop this year. Now again, nothing changes about wheat, but we can produce less rice than we did before. And so again, we sort of put our finger on wheat and we squash down the rice side of things. And we end up with these big gaps over here on the left and these small little gaps over here on the right. Same idea works if something changed about wheat. You could just put your finger on rice and stretch out the wheat axis to make it look better for wheat, or squish it in to make it look worse for wheat, so you can produce even less. And again, we can think about how will this change what we actually choose to produce. Let's say that we were producing at this amount before. Okay, and we get that new rice machine in. We can produce more rice than we did before. But again, we can move to any point on this new production possibility frontier. We could decide, maybe we're going to get a little bit more rice and a little bit more wheat. So we have an interesting result here already, which is that an improvement in the production for rice could end up also increasing the production of wheat, right? Even though it had nothing to do with the production of wheat, we still could end up with more wheat as a result, because basically we have this new production possibility frontier. We have all this capacity to increase our wheat production if possible, if we want, right? We can produce the same amount of rice we could before with less input. We could take some of that leftover input and move it and make a wheat farm and produce a little bit more wheat. All right, that's all we've got. So just a quick recap of what we went over. We talked about opportunity costs and how we can calculate opportunity costs for individual tasks. And we can use the idea of comparative advantage to allocate tasks to the people, firms, or countries with the lowest opportunity cost so that we can most effectively use the resources and inputs that we have. When we do this, we are going to be using our resources most efficiently as possible, and we're going to end up increasing our production over what we would have if we were not trading with each other at all. We also talked about comparative advantage. We make sure that whatever happens, whatever those two tasks are, even if somebody is better at you than both of them, you will still have something to contribute, right? You will always have a comparative advantage, even if you don't have any absolute advantages. We took that idea of comparative advantage and we put it into a production possibility frontier, showing how a person or two people or three people or a whole country could determine how much they can produce by putting together a production possibility frontier that describes their production capacity. We arranged it according to the principle of low-hanging fruit, where those shallow slopes went up top and the steepest slopes went to the right. Because the shallowest slope gives us the lowest opportunity cost for whatever thing is on the x-axis, and we want that person to do that thing first, and so we put them up top. All right, that is it. Thank you very much, and I will see you next time.